Hello everyone, welcome to this lecture on Jackknife for Statistical Computing Stat 3150. The objective for this lecture is to learn how to use Jackknife to estimate the bias and standard error of an estimator. So here's the motivation. In the previous module, when we talked about Monte Carlo simulations and Monte Carlo integration, we saw how we could perform estimation and hypothesis testing using simulations. And the main idea was that you can simulate the data from a fixed distribution, then compute your estimate or your test statistic, and then repeat the simulation again and again to get an approximation for the sampling distribution. And once you have an approximation for the sampling distribution, you can derive all sorts of statistics. You can find the mean, and therefore the bias for your estimator. You can find the standard error, etc. And this approach can be very powerful when studying the behavior of estimators or when comparing multiple testing strategies. And we did look at this, and this is the basis of a lot of statistical research nowadays. However, there is a big obstacle in applying these methods for data analysis because we're making a big assumption. We're assuming that we know the data generating mechanism. We know the distribution of the data so that we can generate new samples out of this distribution. And of course, in data analysis, we rarely, if ever, know the distribution. And so how can we apply these same principles but for data analysis? And in this lecture and the following ones, we'll talk about resampling methods, which are exactly addressing this problem. How can we use the same ideas but in the context of data analysis? So we'll study resampling methods for the next 3 modules, and we'll see how they can be used, again, for data analysis. So the first resampling method we'll talk about is Jackknife. And Jackknife is kind of an old method. It was first introduced to estimate the bias of an estimator. And here's the idea. So we start with the sample of size n, so x1 up to xn. And from that sample, we can compute some sort of estimate theta hat for a parameter theta. And we're interested in estimating the bias. So we're interested in estimating the expected value of theta hat minus theta. Recall that if theta hat is unbiased, then this is 0. So for each I, from 1 to n, we can actually create another sample from the same distribution by omitting the ith observation, right? So we get n samples, each of size n minus 1. And we get those by removing one at a time, one observation. And for each of these samples, we can compute the estimate using the same formula for theta hat. And we'll call this estimate theta hat sub I in parentheses. So now what we have is essentially n plus 1 estimates. And they're all sort of coming from the same distribution. So we can use this to gain information about the sampling distribution of theta hat. And in Jackknife, the formula for estimating the bias is as follows. So the estimate of bias using Jackknife is n minus 1 times the average of all of the estimators that we got by removing one observation at a time minus theta hat. Right? Remember that we get, yes, so that's the definition. That's the formula for the bias estimate using Jackknife. So let's look at an example of how we can apply this and how useful it can be. So consider the following 2 estimates for the variance. So there's, you've seen those 2 estimates before. The one on the left is the one you get from maximum likelihood estimation. And so it's the sum of the squared differences between xi and the sample mean, x bar, divided by n. And we have the other estimator on the right, which we know is unbiased. That's usually the way it's motivated. And the main difference is that we divide by n minus 1. So the only difference is the constant in front of the sum. So we know that sigma 2 hat, sigma 2 squared hat, is unbiased. We know that sigma, so the one on the left, sigma hat squared 1, is biased. So let's use Jackknife to compute the bias, or estimate the bias. So we'll use the formula. We're actually going to generate a little bit of data so that we can actually compute exactly the bias, like the theoretical bias. And so we can hopefully get a sense of whether the estimate from Jackknife is accurate or not. So we'll fix the sample size at 20, and then we'll generate from a gamma distribution using the R gamma function. We'll fix the two parameters as follows. The shape parameter will be equal to 3, and the rate parameter will be equal to 5.5. You can change those numbers. Feel free to do so and see what happens to the bias when you do that. And so the first thing we'll do is we'll compute the estimate theta hat. So the one that was on the left, which was the sum of the squared differences between x bars and the sample mean x bars, and then divided by n. So we can get this by using the mean function, which of course will always divide by n. And so we get an estimate of the variance. We're calling it theta hat. And then we can compare this to theta, which we actually know because we know what the theoretical variance is for a gamma distribution. And in this case, it's the shape parameter divided by the rate parameter squared. And so we can compute those two, we can compare them, and we can see that the estimate is slightly lower than the theoretical value by about 0.04, which is significant here because, of course, the estimate is 0.06, so 0.04 is over 50% of the estimate. So let's see if we can actually estimate accurately this difference between the estimator, the value we got from the estimator, theta hat, and the theoretical value. So let's follow the definition. So we'll create a vector called theta I hat, which will have length n, right? It has to have the same. We're recomputing the estimate by removing one observation at a time, so we'll need to store those n values somewhere, and we're creating that vector theta I hat. And then we're going through a for loop. So for I in 1 to n, the first thing we're doing is removing the ith observation, right? So x vars jack is x vars minus I, so it's a vector of length n minus 1. Then we're computing the sample mean of this new sample of n minus 1 observations. So mean I is the sample mean of the sample. And then theta I hat I, so by removing the ith observation, we get by using the same formula as above. So we're taking the sample mean of the squared differences between x vars jack and the sample mean I. So we're going through this for loop and we get n new estimates of the variance. And once we have those estimates, we can plug them into the formula for the bias estimate using Jackknife. And if you remember, the estimate is n minus 1 times the average of all of the Jackknife estimates minus the estimate we got using the full data set. And if we do this, we get negative 0.003. And so we can, now that we have an estimate of the bias, we can actually debias our estimate by removing the bias, essentially. So what I call the debiased estimate is theta hat minus bias. And then let's compare this to the unbiased estimate, which is the usual sample variance that we compute using the function var. And when we compare those two quantities, we actually see that we get the same thing. So we removed the bias here, and that bias was enough to give us back the unbiased estimate. That won't be the case all the time for Jackknife. It turns out that this is a very special example. But you can see that we effectively did remove the bias, and we got the same estimate as the unbiased estimate. So that was the first example where we wanted to sort of understand the properties of the Jackknife, so we simulated some data and we were actually able to compute the theoretical variance. Now let's look at how we can apply those same ideas but for a data analysis. So let's consider this example. There's a data set called patch in the Bootstrap package, and what this data set contains is measurements of a certain hormone in the bloodstream of 8 individuals after wearing a patch. And so there's two types of patches. There's an old patch, there's a new patch that was developed, and then you actually have a patch, if you will, which is a placebo. So there's 3 different measurements for each individual. And the parameter of interest in this particular study was the ratio of differences, defined as follows. So theta is the expected change or the expected measurement of the hormone when using the new patch minus the expected hormone measurement when wearing the old patch. So that's the numerator. And then the denominator is the expected value of the hormone measurement using the old patch minus the expected value of the hormone measurement when wearing the placebo. And the idea here is that if theta is greater than 1, it means that the change between new patch and old patch is larger than the change between old patch and placebo. On the other hand, if theta is less than 1, the opposite is true. And then if theta is negative, then this would essentially mean that expected value of new patch is less than the expected value of old patch, assuming that the denominator is positive. And so a theta that is actually negative would be an indication that the new patch is worse than the old patch. So that's the parameter of interest. We're interested in measuring or estimating this parameter. And we're also interested in assessing whether the estimate that we'll consider on the next slide is biased or not. And so let's load the package Bootstrap and have a look at the patch data set. You can see that it contains 8 observations, right? We said we only had 8 individuals. And there's 6 variables here. There's a subject ID, which we'll ignore for the purposes of this example. Then there's the hormone measurement with the placebo, the hormone measurement with the old patch, the hormone measurement with the new patch. And then Z and Y are differences, pre-computed differences. So Z, for example, would be, I think it's old patch minus placebo, and Y is new patch minus old patch. And so, yeah, that's right. That's what I wrote here. And one key thing is recall that the expected value of a ratio is not the same thing as the ratio of expected values. So even if we have unbiased estimates of both the numerator and the denominator, which we typically do because those are expected values, and we know that the sample mean is an unbiased estimate of the expected value. If we take the ratio of those unbiased estimates or estimators, in general the ratio will be biased, right? So there's no reason to expect that the ratio will be unbiased. So we're interested in measuring that bias or estimating it. So let's dive in. First of all, we can estimate theta. So theta hat will be the sample mean of patch $Y divided by the sample mean of patch $Z, right? So y is new patch minus old patch. And the expected value of a difference is actually the difference of the expected values. So this is a valid estimate of theta hat, of theta. And then let's use Jackknife to estimate the bias. So this computation will be very similar to what we had on a previous slide, except that now what we have is a data set as opposed to just a vector. And so first we'll save the value n, which is the number of rows of the patch data set. And then theta I, we're going to pre-allocate the memory just as before. So a vector of length n. And then we're going through a for loop, I in 1 to n, and recomputing our estimate. And now we're doing it in one line. So if I just go through each component here, we get mean of patch minus I comma y. So patch bracket minus I will take all the rows except the ith row. And then if we do y in the second position within the brackets, this will take the column y. And so effectively we're taking a subset of all of the data set, and then we're selecting just one column. So mean patch bracket minus I comma y is the sample mean of it's the numerator of our estimate for the data set where we've removed the ith observation. And then similarly for mean patch bracket minus I comma z. And so we're looping through all observations, removing one at a time, and then recomputing our estimate. And if we do that, now we can compute an estimate of the bias, which is going to be n minus 1 times the sample mean of all of the theta i's minus the theta hat, which was the estimate on the whole data set. And this estimate now we can see it's 0.008. And therefore we can compute a biased estimate, so that's the original estimate, and then a de-biased estimate, theta hat minus bias. And we can see that both are actually negative, which means that the new patch is less effective than the old patch. And again, the bias is significant because it represents about 11% of the estimate. So removing the bias actually has a big impact. And then just as a final note, be careful that the ratio of the sample means is not the same thing as the sample mean of the ratios. If we take the sample mean of the ratios, we actually get something positive here, 0.03. So be careful about this. Okay, so that was how to use Jackknife or resampling to estimate the bias. And then later on, Jackknife was extended also as a way to estimate the standard error of our estimate. And here the definition or the formula is a bit more involved, but it involves the same quantities as before. So what we can see is that we're taking the square root here for the standard error, and then we have n minus 1 over n times the sum of essentially squared differences again. But now what we have is theta hat I, so the estimate with the ith observation removed, minus the sample mean of those estimates. And so this is the formula. So let's look at an example of how to apply it. And we're going to start by applying it to our the example from the patch data set. So as I mentioned, we're still using all the same quantities we previously computed, right? So we don't need to go through the Jackknife again. We just need to go through the formula. So here I'm taking the square root of n minus 1, and then in the formula there's divided by n, but instead of dividing by n and taking a sum, I'm just taking the mean here. So the mean of the square differences, theta I minus the sample mean of the theta i's. So what we get is, again, an estimate of the standard error, which is about 0.1 or 0.11. And then using the central limit theorem, we can use that estimate to construct a 95% confidence interval for theta. And so our lower bound is going to be theta hat minus the bias. Right? Remember that we want to remove that bias. And then plus or minus 1.96 times the standard error. And notice here I'm not dividing by square root of n. So the square root of n that we typically see in the denominator is already built into this estimate. So we don't need to divide by square root of n again. In any case, what we get is this following confidence interval, going from negative 0.29 to positive 0.13. And so even though our estimate was negative, we can see that it's not significant. So we would not reject the null hypothesis that that the new patch is worse or is the same as the old patch in terms of average effect. Okay, and then let's look at a second example, which is a bit different, and we'll be revisiting that example in the next lecture. So we'll consider the law dataset in the Bootstrap package. And what the law dataset contains is information on average LSAT and GPA scores for 15 law schools. So each row is a law school, and then the LSAT value is the average LSAT score for students in that law school. And what we're interested in studying or measuring is the correlation row between these two variables. So let's look at the data first. So it's a data frame, 15 observations, and only 2 variables. So it only contains those 2 measures. So first of all, let's estimate row. And we'll take the sample correlation for this. Easy enough. So row hat here is about 0.78. So the correlation is relatively high. And so first, let's compute all of the Jackknife estimates. So again, this code is very similar to what we saw earlier. I'm saving the value n because I want then to create or pre-allocate memory. So a vector of length n, I'm calling it row I. And then I'm looping through I in 1 to n and computing the correlation between the LSAT scores and the GPA scores for the subset where I'm removing the ith row, so the ith observation. And so first I can use this to compute an estimate of the bias. So we can see that the bias here is not too bad. It's about negative 0.006, but it doesn't hurt to remove it anyway. So the biased and the debiased estimates are on the slide here. So the biased estimate was 0.77 or 78. The debiased estimate is also 0.78. So up to 2 decimal places, they're the same. Next, let's estimate the standard error and use it to construct a 95% confidence interval. So again, I'm using the same formula as before. I get an estimate of the standard error for row hat, which is about 0.14. And again, this already includes the factor of square root of n inside of it, so you don't need to account for that. So when I construct a 95% confidence interval, I'm taking row hat minus bias plus or minus 1.96 times the estimate of the standard error. And what I get is the following. So the lower bound is 0.5 and the upper bound is 1.06. And the first thing you should notice here is that correlations are cannot take larger values than 1. So the upper bound here is actually too high in some way. And this is a consequence of the fact that the central limit theorem here is not a good doesn't give us a good approximation of the sampling distribution. There's a lot of skewness, as we'll see later, in this distribution, and therefore this is not a good or an accurate description of the sampling distribution. Okay, so those were the 2 main things I wanted to discuss about Jackknife and the 2 main quantities that you can estimate using Jackknife. And so, as final remarks, Jackknife is a simple resampling technique to estimate bias and standard error. And again, the idea is very simple. You're removing one observation at a time and recomputing the estimate. And so what you're essentially doing is getting new samples from the sampling distribution or a similar sampling distribution. There's a lot actually of theoretical details behind the Jackknife, which are beyond the scope for this course. But I just want to make two important observations. So the first one is that the d-bias estimate is generally not actually unbiased, but more accurately, it's asymptotically unbiased. What this means is that when you remove the bias estimate, the bias will go to zero more quickly than the bias from the original estimator, but it's not necessarily zero, right? So it will go to zero and more quickly than the original estimator. So that's the first key thing. So you actually gain something from using the de-biased estimates. And then the Jackknife only works for estimators that are called smooth plug-in estimators. I won't go into the definition of what this means, but as a consequence, it means that Jackknife actually does not work with the median. And we'll look at an example of this in the next lecture. But that's a known limitation of Jackknife. And then Jackknife was generalized in two important ways. So it's more of a historical method than something that's used very often in practice. The first way in which it was generalized is the bootstrap, which will be the topic of the next lecture. And then you can say it's also related to cross-validation, which is a way to estimate prediction error and prediction quantities. We won't talk about cross-validation in this course, but it's an important topic in a lot of statistical research or statistical methods. And in particular, you'll probably encounter it in our statistical learning course, 4250.